We are now talking about fluids, fluids at rest and in motion. What happens to fluids when they are at rest and when they are in motion? What properties affect them? Okay, let's start from fluids at rest and in particular water as a liquid at rest. When we have a bowl of water that is at rest, that's stagnant water. Mosquitoes can actually walk on it. Mosquitoes can actually lay their eggs, that is larva, on it, and it stays there, hatches, provided that this body of water keeps on being at rest over the period of time it takes that larva to hatch. Why is it that the mosquito can walk through without sinking? Why is it that they can lay their eggs on this body of water without the eggs sinking? The eggs stay there, hatch, come up, and leave. Why? Why is it that when we place a piece of needle on the top of this water, when we place it carefully on top of this water, it's going to rest there without sinking? Why is it that if this water is in a dusty environment, dust actually settles on the top without affecting the liquid below the surface of this bowl of water? Why? So this is the phenomenon we call surface tension. We can define surface tension as the force which acts as the liquid surface, which making the liquid surface to behave as if it is a stretched elastic skin. So how can we explain this phenomenon using physics? We know that this water is made up of molecules, that's molecules of water. Let's represent them with these circles to represent the molecules of water. They are at the surface, they are within, they are all over the water body. Now, these molecules have intermolecular forces. That is the force of attraction between the molecules. Each of the molecules are attracting each other using a particular force which we call intermolecular forces, including the ones at the surface. Now, for the top molecules, the molecules at the surface, they can only use their intermolecular forces to attract fellow molecules of water. Now, since they are at the boundary between the air and water, they can only attract their fellow water molecules. The intermolecular forces are not there to attract air molecules above them. So we have excessive force, kind of, in a way. We have an excess of force that is still remaining within them. Like they should form bonds or forces of attraction between water molecules. Now they are in between air and water. Part of them have been used to attract their fellow water molecules below here, but the forces available above this surface to attract fellow water if there was other water molecules above them, they will now double up. They will now strengthen, they will now have more forces to attract each other. Like that, the force that should have been used to attract molecules above this water surface is now doubled up to be used for attracting each other. Therefore, the force available at the surface is greater than this force available at any other part of this water body. I hope you understand that explanation. That is why we have something called surface tension. The force at the surface of a liquid is actually stronger than the force at any other part of the liquid because the intermolecular forces that should have been used to bond the molecules of the liquid, those ones above here double up to form bonds, stronger bonds with each other. That is why the liquid surface will now appear to act as if it were made up of an elastic skin. That is why mosquitoes can walk on it. That is why when we carefully place a piece of needle or pin on the surface of the water, it can actually rest there without sinking. That is why dust can settle on the surface of a liquid without sinking, because there are forces on the surface of that liquid that are used to, that strong forces, combining forces, bonding forces. They are not bonding with the surface, with anything that is on the surface of the liquid. They are just bonding with fellow water molecules. Okay, that is what we call surface tension. Now, where do we apply surface tension in real life? Surface tension has its application in waterproof materials like umbrellas, raincoats, and the rest of them. So, umbrellas and raincoats are treated with oil-based substances that will actually have a high surface tension to prevent water from soaking into the umbrella. And it also has its application in the use of detergents and soap in cleaning things like washing plates, washing clothes, because the oil and detergent actually reduces the surface tension of water, making water to be able to seep through the clothes to now dissolve the dirt in the clothes, and then they can now be washed out. We can now ask, since we've already started seeing factors which affect surface tension just by stating its applications in life. So, addition of detergents and soap affects surface tension. That is, addition of impurities into that liquid affects surface tension. And we can also see increasing the temperature of a liquid affects its surface tension. When we increase the temperature of a liquid, it reduces the surface tension on that liquid. So, hot water will clean your clothes better than cold water. Soapy water will clean your clothes better than just pure water. Then, we also have shaking that body of water. That is, when we shake the body of water or when we touch it, it's also reducing the surface tension. We are now breaking that very strong bond that has been formed at the surface of this body of water. So those are the factors that affect surface tension. Also, the nature of the liquid also affects surface tension. The type of liquid we have. Some liquids have a higher surface tension than the other ones. So, nature of liquids, temperature, shaking the water, and addition of impurities such as even oil, detergents, soap affects surface tension. So we've seen how to reduce surface tension. Now let's talk about something we call capillarity. For that, we are going to draw two bowls containing two liquids, two different kinds of liquids. This is water. This is mercury. And we are going to place tubes into these liquids. A very thin one, a medium-sized one, and a large one. Now, when we place these tubes inside this, we are going to notice that for water, the liquid will rise, the water will rise at different levels for these different sizes of glass tubes. Then for mercury, we are going to notice a fall below the surface. This is rising above the surface. This is a fall below the surface. And the fall kind of varies according to the size of the tubes. So this is what we call capillarity. Capillarity is the rise or fall of liquids in a narrow or capillary tube. Now, why will certain liquids rise in capillary tubes, and why will certain liquids fall below their level in capillary tubes? This will introduce us to two forces. We have cohesive force, and we have adhesive. Cohesive force and adhesive force. Cohesive force is the force of attraction between molecules of same substance, while adhesive force is the force of attraction between molecules of different substances. Now, how do we remember which one is cohesive, which one is adhesive? We've already heard of adhesives before now, right? We hear of adhesives as glue. What do we use glue for? We use glue to join two different materials together. So that is what we are going to remember, that adhesive forces are forces of attraction between molecules of different substances. That's like gluing two different things together. Now, for cohesive force of attraction between molecules of same substance. So co is talking about same things. Something like we say co-tenants. That means these tenants are living in same house. We have something like co-debaters. That means these debaters are debating together. Or anything, cohabit means we are living together. So co means together, means the same, something of the same. So cohesive force of attraction between molecules of same substance, and adhesive force of attraction between molecules of different substances. Now, how does these two forces affect the rise or fall of liquids in narrow or capillary tubes? That's capillarity. Now, let's start with water. Water. Each of these liquids has these two different forces. A force of attraction between molecules of water, that's cohesive force, and force of attraction between molecules of water and the molecules of the glass tubes that we have here. Now, for water to rise in this glass tube, it means that the adhesive force between the molecules of water and the molecules of this glass tube is greater than the cohesive force among the molecules of water. That is, this looks like just those siblings that you have that rather care for their friends, that's outsiders, than care for their fellow siblings. That's how water, the forces of water. So they have a stronger bond with outsiders than having a stronger bond with their fellow water molecules. So they rather rise in this glass tube than stay with their fellow water molecules. Though may not look similar, but that's just how I view it in my mind. So always remind me that cohesive force is actually less than the adhesive force for a liquid to rise in a capillary tube. Then look, coming over to mercury, we see that it is now the opposite. The cohesive force between the molecules of mercury is stronger than the adhesive force between the molecules of mercury and the glass tube, the narrow glass tube. Now, this is like those people that prefer family to any other thing. So they rather bond with each other. So they don't want to play with the outsiders, which is the glass tube in this case that has come into this liquid container. So they rather stay with each other. So they rather fall. They prefer to stay with their fellow molecules because the cohesive force is stronger than the adhesive force with the glass. So they fall. They rather fall than to rise. Now, when we look carefully at the surface of the liquid at these capillary tubes, we are going to notice the shape. This has a U shape and this has an inverted shape. That's an N shape, small letter N shape. We call this concave meniscus. Concave meniscus. And we call this convex meniscus. Now, how do you always remember which one is concave and which one is convex? It depends on the liquid surface you're looking at. when you have your eye here, you as an observer, you have your eye here. You're staring into the capillary tube. You're looking at the shape formed by the liquid at this capillary tube. You are going to notice this U shape. It's an upward shape. Now, you can see it is caved in from your point of view as an observer looking from this liquid surface. When you have your eye here, as an observer, observing this liquid surface, you're going to notice the bent shape, the downward shape of the liquid. That is convex meniscus. It is vexed out, it is curved out. So that is what we call convex. It is out. This is cave, inward. This is outward, convex. It is vexed out. Okay, so that's how to remember the names of the shape formed by the liquid at the top. That's the meniscus formed. Now, we've seen the forces that causes this. So sometimes you'll be asked, why does water rise in a capillary tube? You just say, water rises in a capillary tube because the adhesive force between the water molecules and the glass molecules is stronger than the cohesive force between water molecules. Also, why does water wet glass? And also, why does water form a concave meniscus? They are all same reasons. For mercury, mercury falls in a capillary tube, or mercury does not wet glass, or mercury forms a convex meniscus because the adhesive force between the molecules of mercury is stronger than the, did I say adhesive? Sorry. The cohesive force between the molecules of mercury is stronger than the adhesive force between the molecules of mercury and the glass tube. So that's all about capillarity. And then we have capillary actions in nature. Now, it is because of capillarity, that's why the roots of trees can absorb water from the soil and the water rises in the stems of trees. Because of the capillary action of water, water tends to rise in narrow or capillary tubes. That's also how we have exchange of blood. That's the flow of blood in our body vessels. We have our capillaries. So through the veins, the arteries, now the capillaries. That is where we have all those exchange. Blood can actually flow and liquids exchange in our bodies because of the action of capillarity. Now, also when we have blotting paper, ink rises in a blotting paper because of capillary action. And also, when we have kerosene lamp or kerosene stove, the kerosene liquid rises in the wick of the lamp or the stove because of capillarity, the capillary action of the kerosene, and so on and so forth. So, this is all about liquids at rest and in motion. And we'll now be talking about something we call viscosity. Since we are talking about liquids in motion, viscosity, the resistance to flow of liquids, that's friction in liquids, viscosity. The resistance to flow of liquids. Viscosity is actually the resistance to the flow of a fluid. And when we say fluid, we are talking about liquids or gases. Friction in fluids. Now, the more viscous a liquid is, the slower it is going to flow. The less viscous it is, the faster it is going to flow. Something like when we have something like honey and water. We know that honey is going to flow, like when we have an inclined plane like this, and we pour water here, like we pour water here and we pour honey here. We notice that water will flow faster, water will run faster to come to this ground. Then while honey will come later, like honey will flow slowly. So we see that honey is more viscous than water because honey flows slowly. It is more viscous. It has more resistance to its flow. The resistance to flow of a fluid is called viscosity. That is friction in fluids. Okay, now we have factors that affect the viscosity of fluids. What factors can make a fluid to flow faster? What factors can make it to flow more slowly, more sluggishly? We have the nature of the liquids, of course. The type of liquid also affects the flow. We also have temperature, a very, very big factor in the viscosity. The higher the temperature, the lesser viscous it is. Because if we should heat up something like oil, something like it melts, it can now flow faster. We have the concentration. The higher the concentration, the more viscous that fluid is going to be. We also have pressure. Though pressure affects gases more, affects the viscosity of gases more than it affects the viscosity of fluids more. Like it doesn't really change the viscosity of fluids, though it still affects it, but it's just very, very minimal. It affects gases more. And we also have presence of impurities. Impurities can affect the viscosity of fluids. And now, the effects of viscosity. We've said viscosity affects how fast or how slow a fluid is going to flow. And we also have, it also affects how fast an object is going to move inside a fluid. Let's say we have this viscous fluid and we throw a ball bearing, a piece of ball bearing inside this liquid, this viscous liquid. We'll see how many forces are affecting it. We see the weight, of course, is pulling this ball bearing down, and a force we call upthrust, which is due to the displaced fluids as this ball is falling into this water. So we have upthrust, we have weight, and of course, viscosity, the resistance to flow, the resistance to motion, that's friction in fluids. So we have three forces acting on this ball. We have upthrust acting upwards, viscosity, that's viscous force, acting upwards too because it's opposing the motion downwards, and we have the weight acting downwards. Now, at a point, as this ball is falling, it is falling with an acceleration. And then at a point, the downward forces is going to be equal to the upward forces. And at such points, we say we've attained something we call terminal velocity. So it is a constant velocity. It is the highest velocity attained by an object falling or moving through a fluid. So it is attained when the viscous drag or viscous force is equal to the downward force, which we can equate it to the weight minus the upthrust. Or we can also say when the upward forces, that's viscous drag plus the upthrust, is equal to the weight. So when we send this over, since we are interested in talking about the viscous force, so we make the viscous force the subject of the formula here. So this is the moment where we know we have terminal velocity. And this is the reason why rain does not hit us as if they were falling stones from heaven. Like if at a point the raindrops do not reduce their acceleration, like the acceleration don't come to zero. If not, the raindrops would have been painful, really painful for us. And the same thing happens with those people that are doing skydiving. They also put up the parachutes so as to take advantage of upthrust and viscous force of the air, the viscous drag of the air, and the upthrust too of the displaced air as they are falling through. So they take up that advantage so as to reduce the speed with which they will fall eventually. Okay, that's about terminal velocity. Now, we said that viscosity is the friction in fluids. Now, between solid friction and liquid friction, that's viscosity. Do they have similarities? Do they have differences? Of course, they have differences. Viscosity is in fluids, while friction is in solids. That's just so obvious. Now, friction does not depend on the area of the surfaces in contact, while viscosity depends on the area of the surfaces in contact. Then for similarity, both of them, they oppose motion, of course, and they depend on the nature of materials in contact. The nature of the surfaces in contact affects both viscosity and friction. We will now answer some questions to be able to test our understanding. Which of the following liquids has the highest surface tension? Soapy water, cold water, hot water, oily water. Now, let's look through our options and then see which one we are going to pick out. Soapy water. We've already added something that reduces surface tension to it, so it can have the highest surface tension. Cold water. Well, it has a low temperature, meaning high surface tension. But let's move on. Hot water. High temperatures reduces surface tension. So no, it has a low surface tension. Oily water, we said the presence of impurities reduces the surface tension. So oil will actually reduce the hydrogen bonds as intermolecular forces of water. So all these three, the surface tension has been reduced. So the option that is the correct answer is cold water. It has low temperature and no impurity. So it has a high surface tension. Number 2, the rising of a liquid in an open-ended glass tube of narrow bore is it osmosis, adhesion, surface tension, capillarity? I know you know the answer, capillarity. That's the rising of a liquid in an open-ended narrow tube. Though surface tension, the force surface tension also affects that rising, because when the liquid rises, it is the surface tension, the force, that holds it up there. It only rises as much as the surface tension can allow it to rise. But the reason why it rose is because of adhesion, cohesive forces, that interaction, that's the capillarity. That's what affected it. So, capillarity. Now, let's go over to the next question. The property of a fluid that is used to determine its suitability as a lubricant is it is not the capillarity, not the density, not the surface tension, it's viscosity. Actually, viscosity determines whether we are going to use a fluid as a lubricant or not. So finally, before we go, let's have this. In which of the following is surface tension important? The floating of a ship in water. When we look at the floating of a ship in water, it's not really surface tension that makes the ship to float. It is actually the law of flotation. The ship was able to displace an amount of water that is equal to its own weight. So that's law of flotation taking place, not because of surface tension. Floating of a dry needle in water. We talked about this when we talked about surface tension. So really, this is a surface tension effect. But let's just keep it aside and move further. The floating of a balloon in air. This again is due to the law of flotation. The balloon is floating in air because the balloon has been able to displace an amount of air equal to its own weight. So that is why it is floating, not because of the surface tension of air. And surface tension actually occurs in liquids, not in gases. The diffusion of a sugar solution across membranes. This is actually diffusion. So this has nothing to do with the surface tension. So the option that is correct is the floating of a dry needle in water. This is where surface tension is the effect of, that's the cause of this occurrence.